You've done this stuff before?
Yeah, I like remember this.
From Calc 2?
Yeah.
Okay. You did numerical integration in Calc 2?
Yeah. I mean, not numerical as well.
Yeah, but I mean, analytical fine. Is this new? Riemann sums?
Yeah, I knew a little bit of midpoint, but like, what was the sum one? The one that we just talked about.
Rectangle, midpoint, Simpson.
Simpsons rule. Like I've never heard of Simpsons.
All right. Yeah, you never usually use rectangle or midpoint. Either at the least you use trapezoidal rule, or Simpson's rule is the max you would want to go. Beyond.
Oh yeah, we talked about that.
Yeah, I'll go over trapezoid next. All right. Okay, so let's keep going with integrating. And just a quick reminder, we were talking about finding the area under the curve. Here, we are working with a very simple function, but you would use the same exact concepts when finding area or volume for a hull. All right, analytically, we figured out exact value of area is 1 unit squared. Then we were trying different numerical rules. So first, rectangle rule, one way gave us a 57% error, another way gave us a 100% error. So you almost never want to use the rectangle rule. The next best option, but still not a very good one, is midpoint rule. Okay, there if you remember, we just take the midpoint and form the box, the rectangle, using that height. And we get an 11% error. Next, let's do the same thing, but with trapezoidal rule. So all right, and if you remember, the only thing that we need to do is we need to draw a straight line between the 2 points. And then whatever is enclosed within this trapezoid, in this case, it turns out to be a triangle because this height is 0, but in general, it'll be a trapezoid. So this area of the trapezoid will be our approximation. And we know how to compute the area of the trapezoid. So area is basically, this is, the width is pi/2. This height is 1 unit, and this height is 0 units. So for a trapezoid, we know it's 0 plus 1/2 times the width, which is pi/2. Okay, and we get pi/4, which is 0.78 something something. All right, so here we get a 22% error. Now you might look at this and say, the trapezoidal rule is worse than the midpoint rule. This is true only because we have taken one discretization, one full box. If we start cutting it up into smaller trapezoids and cutting this up into smaller boxes, very, very quickly, the trapezoidal rule will become much more accurate. This is related to order of accuracy, which I'll tell you about in a few minutes. All right. And then the last one we have is Simpson's rule. Let me just make sure, yeah, mic works. So Simpson's rule. All right, with Simpson's rule conceptually, what we're doing is we are taking 3 different points, A, B, and halfway through, A plus B over 2, and we basically try to draw a parabola through it. Okay, so my drawing is bad in the sense that the parabola seems to completely coincide with the sine curve, but obviously that will not be the case. So there will be some difference. All right. And let's plug in the Simpson's rule formula. So let me just remind you, the area will be delta x over 6 times f of a plus 4 midway plus f of b. All right. I'm not going to write the numbers. You're going to help me figure out what each of the numbers are. What's this guy, delta x? Pi over 2. Yeah, go from 0 to pi over 2. So we write pi over 2 minus 0. Okay, fine. Over 6. What is f of a? Okay, remote students, what's f of a?
0.
Because?
It's the first point on a sine wave at the 0.
Yeah, so f of a would be just sine of 0, right? X equals 0. So we write sine of 0. What about the next one? What do we write for f a plus b over 2? This is not f times a plus b over 2. It's f evaluated at this x value. Okay, so what do we write for this?
Root 2 over 2.
All right, so one step before that, in terms of sine, how do you write this?
Sine of pi over 4.
Yeah, sine pi over 4. We're looking at the midpoint, a plus b over 2. A is 0, b is pi over 2. So we're looking at x equal pi over 4. So we have sine pi over 4. All right, and the last one is sine of pi over 2. F of b, b is pi over 2. We just plug in pi over 2 in place of x. Remember, this is f x equals sine x is the curve. Okay, so once you plug in all the numbers, you get, let's see, pi over 12 times 0 plus 4 over root 2 plus 1. And when you compute this, it's 1.002. Okay, so this is 0.2% error. Okay, so just with a single, not a box, just with a single discretized element, we are almost perfect. If you start cutting this up into smaller and smaller segments, you'll get almost 1, which is the correct answer. Okay, so now in reality, you never really take just one discretization. You'd write a program and do this in a for loop. So let's do this on paper first. Let's do the trapezoidal rule for 2 discretizations, not just one. So it becomes completely obvious how you would do it. All right, so let's do, let's now integrate sin x from 0 to pi over 2 using 2 subdivisions. And the trapezoidal rule. Go from 0 to pi over 2. All right, what do you think we should do? All right, perfect. Let's look at the midpoint and cut it exactly into 2 equal subdivisions with respect to the x-axis, of course. So pi over 4 is our midpoint. What next? What would you do next after this? We're using the trapezoidal rule, yes. Not square, the first trapezoid and the second trapezoid, right? So we form the first trapezoid by joining point 1 and point 2 here. That's our rectangle. Then we have another trapezoid here. Point number 2 and point number 3. That gives us our second trapezoid. And then we find the individual areas and sum them up. That's it. So if you were to write a MATLAB program, you would do this in a for loop. Right, so area is equal to, first trapezoid is sine of 0, the sine of pi over 4 over 2 times delta x, which is pi over 4. And, well, we'll make it more explicit like this. And the second trapezoid is sine of pi over 4 plus sine of pi over 2 divided by 2 times delta x is pi over 2 minus pi over 4. Is this okay, what I wrote here? Anybody miss a step? It's just FA plus FB. For the first trapezoid, FA corresponds to 0, FB corresponds to pi over 4. For the second trapezoid, FA corresponds to pi over 4, FB corresponds to pi over 2. So same formula for the 2 independent shapes. Okay, and when you do all of this, you'll get 0.948. And this is roughly a 5.2% error. So just to compare this two subdivisions to what happened with one subdivision, look at this, 22% error has now become a 5% error. Okay. So you can imagine if I do even more subdivisions, how quickly this error will keep dropping. And the rate at which this error drops is called the order of accuracy. Okay, and we'll write a few statements, but let me explain first. Let me bring back this rectangle rule, all right? Order of accuracy of the rectangle rule is order 1. What that means is your error drops in proportion to delta x to the power 1. So if I make my delta x exactly half, the error will drop by half. Okay? So if I take two intervals here, my error would be roughly 27%. Okay? Midpoint rule, actually I don't remember if it's first order or second order. All right, so I'm not going to tell you something that's wrong. Trapezoidal rule is second order, all right? Meaning if we divide this interval into half, meaning two exact intervals, so this should drop by roughly how much? So I said this is second order accurate. So error drops as delta x squared. Okay. Delta x divided by 2, delta x squared becomes what? 1/4, right? So the error would drop by 1/4. 1/4 of roughly 20% is roughly 5%. Okay, so if you keep going, if you do 4 divisions, meaning you divide this delta x, you half it another time, so you would have each subdivision goes into 2 further subdivisions. What do you expect will happen? Can you predict what will be the new error? Okay, okay. Let's write it down and it'll become clearer. Is what? Yeah, it'll be this number divided by 4, which is 1.25 roughly. Okay, so let's write this and we'll discuss that just once more so it becomes clear. So order of accuracy. It determines how fast the error in our numerical approximation drops as we decrease delta x, which is the interval width right? And we usually write it as epsilon, which is the error is order of delta x or order of delta x squared the first guy is first order accurate. This second one is second order accurate. Okay, and some examples for the first one, so rectangle rule, all right? So rectangle rule falls under this. All right, okay, and I see midpoint rule falls here. So this is midpoint rule or the trapezoidal rule. You've encountered this notation before, order delta x or order of something? Okay. And so in practical terms, how is this, knowing this useful? It's useful because the first one tells us if an integration scheme is order delta x, it means that the drop in error is proportional to delta x square, yeah, to delta x to the power 1. And for order delta x squared, error drop is proportional to delta x to the 2. You don't need to say drop in error. The error is proportional to. So let me just scratch out the drop. It's proportional. It's not equal. So don't say it's equal to delta x. And as an example, you can see, for instance, for our trapezoidal rule example. So for the trapezoidal rule, we saw that changing delta x to delta x over 2 made the error go from what was it, 22? Yeah, 22% to 5.2%. Okay, this happens because Does this make sense? The error varies as delta x squared. If I drop delta x by 2 times, the error drops by 4 times. That's basically what's said here. Is this okay, everybody? All right, you tell me, if I give you a scheme that's order delta x cubed, that's third order accurate, what happens here? A scheme that's third order accurate and you decide to chop delta x into half, exactly half. No, they won't go to 1/9. Yeah. So if you have a order delta x cubed thing, your error will drop as delta x old over 2 whole cubed. Okay. So you would go to error over 8, which is very good. You drop the error by 8 times, which is almost 1 order of magnitude, just by using more discretizations. All right. So everybody understands this? Tell me now if this doesn't make sense. This is very simple, but it takes a while to sink in. So, and keep this with you. This is usable many different places, not just engineering. So, any questions? You will be able to do this on the quiz or the test. Yes? No? Maybe? Okay, silence means no. All right, everybody online. Tell me, what doesn't make sense here?
It all makes sense to me.
All right, I want one person to say it doesn't make sense. Come on, don't be shy. If I give you this quiz, easy points. You will not miss it, correct?
Yes.
Okay, perfect. Awesome. Okay, so yeah, that's Simpson's rule is third order accurate. I have to double check, but I think Simpson's rule is third order accurate. You can ask Wikipedia, it'll tell you. Okay. Now, if we think about a hull, all right, it's usually it's not a regular shape. It's there's lots of curved sections that we have to deal with. So let's look at let's think about which areas or regions in a ship hull would be associated with the largest errors in our numerical approximation. Let me draw like a very simple, non-realistic hull shape, and then we'll think about what this question is saying. Okay, now, so when you start, if I ask you to compute the area of this hull section, you can think about this as being composed of the forward part and something in the middle or the back, okay? Which part do our numerical integration schemes have the most trouble with? And which part they're absolutely perfect?
They have trouble with the curved parts and are perfect where it's straight line.
Yeah, so if you see, if this is exactly a straight line, there, if you come in and say, I will form a box, you know the exact area of the box, okay? There's no approximations here. The length times width you compute will give you the exact value. But this curved section, if we just use a trapezoidal rule approximation, you see we miss some parts. Not terrible, but we do miss something. So it's always the curved regions where our the new integration schemes have the most trouble. So the answer is in regions of high curvature. Curvature. How do you fix this problem? You say more boxes, more trapezoids? Yeah, so you can say, all right, chop this up into, instead of just two subintervals, chop this up into 10 subintervals, all right? So one remedy is we call it global refinement. So instead of just taking two subintervals, we do many of them. Okay, here is 1, 2, 3, 4. And you form your new trapezoids here, 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 here. You see, we're very close to the correct answer. When you write a program, what does this entail? Going from here to here, what changes in your program? What changes? Yeah, dx it just changes from one value to another, and in the for loop, instead of going over 2 loops, you go over 10 loops, or however many boxes there are here. So it's a very simple change in that sense. Is this efficient? What have you done here to the rectangular part? Is this necessary? Yeah, instead of global refinement, you can do local refinement. So leave the box as a rectangular box because it doesn't need to be fixed. And take the curved part and do local refinements, okay? So this first approach, global refinement, it's easy to code, but it's not very efficient. When talking about all of this in 2D, you don't care. The increase in computational cost is not huge. When you go to 3 dimensions, it can very quickly get out of hand, okay? So if you just increase subdivisions by 10 times, that's what? 10 to the 3 increase in computational cost. So 1,000 times slower computation. Okay. So this approach, the first approach is easy to code. But increases computational cost. Significantly. All right, and the other approach is instead of doing a global refinement, we do a local refinement. So the rectangular part we leave as one subinterval, but the curved part we break up into many subintervals here. This approach is more involved with respect to coding. But it is computationally efficient. Okay. Any questions about numerical integration in general? Does the concept sort of make sense? I can't see your faces, so difficult for me to tell. So say yes or no. Conceptually, does it make sense?
Yes.
Yes.
Or any no? Don't be shy. If we have one no, then there's at least 3 or 4 other no's as well. All right. Anytime it doesn't, or you're still feeling shy and want to talk later, just we'll Zoom later. Just let me know. All right. We've just been talking about computing area using numerical integration. We use the same exact concept for computing moment of inertia, for computing the center of mass. Okay, and if this is clear, all of the other stuff is very easy. This thing extended from 2D to 3D gives us the ability to compute things like volume, center of volume, all right? So equivalent things that we compute for area, we can compute for volume in 3 dimensions. And the only thing that changes, so let's talk about volume integration. Let me see if I have, I think I have a slide here. Yeah, okay. All right, let's just go through this. I mean, this should be all clear by now. We have the curve. We just break it up into smaller boxes. You see the error in our approximation keeps getting better because we don't miss a lot and we don't enclose what shouldn't be enclosed. That's the rectangle rule we talked about. Well, this is the midpoint rule, not the which is a part of rectangle. But yeah, don't call it rectangle rule. This is the midpoint rule. There's the trapezoidal rule we talked about. Okay, volume. So if instead of in 2D, you visualize a surface in 3D. So this could be something you chop off the hull, right? You chop off a part of the hull and that's the curvature it has. What's the volume enclosed by this hull section and the XY plane, okay? Same as we compute area under a curve, you would compute the area under this surface. And the volume integral looks like this, okay? Think about what this is saying. Going from y equal one extreme to the other, x equals one extreme to the other, that's what the integrals denote. We have, let's think about what this means, z times dx times dy. So in this scenario, what does z represent? Z is a function of x and y. What does z tell us for this surface? Yeah, the height. So if I give you a value of x and y, let's say x equal 1, y equal -1. What is the corresponding height at that location? Okay, that's what this tells us. What does dx and dy tell us? Is what?
The volume under the X curve and then the Y curve.
Dx and dy, volume under the x curve, y curve.
DX would be two-dimensional, the DY vector.
Not entirely. So to figure out what dx and dy mean, think about what we did for 2D. What does dx go to when we think about sums? Yeah, width, right? Delta x. So if we were doing this in 2D, dx would just be the width of the interval we take. And the width of the interval is our choice, whether we subdivide this into 10 intervals or 100 subintervals. Here you see the entire surface is made up of these little squares. So what would dx be for the little square? Let's take one square here. What's dx for this guy? I'm not asking for a number, just geometrically, what does dx represent? It represents the width in the x direction. So basically this tiny width near my mouse. What does dy represent? Yeah, that's the other width. If this is a square, both are equal. This is a rectangle, they are unequal. Again, that's our choice, whether we use squares to discretize the surface or whether we use rectangles, okay? All right, now think about this. dx, dy represents the area of this square, yes? Yeah, it does. So dx, dy would be the area, the cross-sectional area of this square. What is the volume under this square? Oops. If I give you the cross-sectional area, how do you compute the volume? For a stick, a square cross-section stick. Multiply by the length, okay? Which is what? Which is this guy, z. Does it make sense now why we have z times dx times dy? It's basically height times delta x times delta y. That gives you volume of one stick. And yeah, can I draw a stick here? Let me see. Yeah, so it's basically, we're talking about this. Yeah, we're talking about the volume of this stick, okay? And when we do integration, again, think about in discretized terms, this becomes a summation. So sum in all the x direction and then sum in all the y direction. Okay, basically summing up all of the individual sticks. That gives us the volume under this surface. Of course, again, we will make a little bit of an error because this square in reality is not a perfect square. We are just approximating it to be a perfect rectangle or a square. So we will either overcount a little bit or undercount a little bit. Is this clear what this means? So volume integral looks scary, but always think about what each term means, and then it becomes very easy to visualize it. Okay, any questions? All right. So yeah, if our surface looks like a saddle, that's just the top part of the solid shown here, the volume would basically be whatever is underneath it. Okay, so volume would be the volume of this whole solid thing. This is the same integral that was on the previous page, and when we change it into a summation, just become summation in the y direction, in the x direction, the height times weight I, weight j. So for the simplest case, these weights would be delta y and delta x. So the first guy, you could say this is delta y, and the second guy, you could say it's delta x. And this is very similar to the rectangle rule. Okay? Remember, when we did Simpson's rule, it became more involved. It was not just delta x times delta y. There were more terms. That's why to keep it more general, we have this wi and wj. Okay, is that okay? Going from the continuous integral to discretized integral in 3D. What if I ask you to do a 4-dimensional integral? What would you do if I gave you a 4-dimensional, a function that was dependent on 3 variables? So here the function is dependent on 2 variables. If I give you f of x, y, z, x comma y comma z, and I ask you to evaluate the integral, what do you do? Yeah, you just do dx, dy, dz, and you have 3 integrals with the appropriate limits. Dx, dy, come on, all right, dz. Okay, and have you ever seen this 3 integrals? You have, right? It's a volume integral. So this you can represent as a dv. And think about this, dv is the volume of, instead of cutting squares, now we're cutting cubes. So delta x, delta y, delta z, it's delta volume. So no matter how many dimensions you're given, you do the same thing, just increase the number of sum signs here. Instead of 2 sums, we would have 3 sums. All right. All right, let's see, what else is here? Oh, okay. So, and there's no one way of doing this. So the first way I told you was you take the square and form sticks. Another way you could think of is, all right, I'll cut this surface up into 2-dimensional slices. So you see the first red area is area under the first slice. The hidden red part is the area under the second slice. If you just take a knife and slice through the surface one by one. Once you know area 1 and area 2, you can compute the volume in between. How? You use the trapezoidal rule in 1 dimension now, okay? So many different ways of doing this. Yeah. All right, okay. All right, so volume integration. Now we have 3 axes, x, y, and z. I don't want to, okay. All right, I'm going to put X here because otherwise it will not be a right-handed system. Yeah, this is a right-handed system. Okay, fine. And let me try to draw something in 3D on this page. Okay, let's see if I succeed. Yeah, so think of this as a surface, a three-dimensional surface hovering over the XY plane. And basically we cut squares and we project the volume enclosed by this small section. This would be your, first this would be delta y, that would be delta x. And of course, this point, the height is z of x comma y. Okay, and you can, if you're more comfortable writing this as z equal f of x comma y, that's fine too. Right, so in this case, volume enclosed between the surface I've drawn, between the surface and the xy plane. So all the way up to the flat plane, we would say this is V is double integral of fx comma y dx dy. That's the continuous form, which is nice if you know the analytical function fx comma y. But if you don't, you have to use numerical integration. So, or in discrete form, it becomes volume is two summations. And another way to write this is, well, a shorter way to write this is f of I comma j dx dy. Is this okay? Does this make sense? I mean, it's the same thing we were talking about on the slide, going from continuous to discrete. Delta x, delta y is the area of this cross section, and fi comma j is just the height of the cross section. So this gives us volume of each individual element that we cut. Okay. So now let's talk about area moment of inertia. Yeah, there's nothing more to volume integration. I mean, you can see going from 2D to 3D, just there's an increase in the number of sums. Going from 3D to 4D, there would be another increase. Going to ND, you would have N sums. So we have, now we talk about area moment of inertia. We mentioned this briefly in one of the classes, but intuitively, what does moment of inertia tell you? Intuitively, what does it mean to you physically? What does it represent? It represents rotation, okay, tell me more. Rotation about a given axis, okay, okay, perfect, perfect. So can you see my pen? No, you cannot. Well, maybe it's better. Okay. So look at my webcam. Actually, let's try and find a YouTube video, and then we'll talk about the stapler. Okay. Ice skating. What is the term? Okay, they call it spin. I mean, I was going to, okay. I just want a simple. Okay, fine.
Hey there! This video will be explaining the physics behind spins in figure skating.
Okay, okay. Aha.
Momentum even before I started spinning by skating on a curve and by pushing with my other leg. So now that that's covered, you may be wondering how I went from skating on a curve to spinning so quickly. This is also down to angular momentum. You may remember L equals...
Okay, so you probably have seen this in your physics classes, and you remember that there's no extra effort that the skater puts in.
This is also down to angular...
The only effort she puts in is when her arms are out and she starts spinning, and then she just brings them in and
momentum. You may remember L...
She speeds up, right? So remember this guy, I, that's the moment of inertia, but mass moment of inertia, not area moment. They are two different things, don't confuse them. All right, think about okay. If she's spinning with the same speed with her arms inside and she bumps into you, versus same spinning speed, same angular velocity with arms out and bumps into you, which one will floor you? So don't think about the change in speed. I'm talking about two different instances. You bump into her while she's spinning with her hands in, let's say 1 radian per second. That's very slow, 10 radians per second. And versus she puts her arms out and spins, same thing, 10 radians per second. Which one will knock you flat? The speed is the same, right? Omega is 10 radians per second. Yeah, when the arms are out, you really want to avoid those fists, okay? The reason is this mass is spinning about an axis that's further out compared to when her arms are in. So the mass moment of inertia is much higher, okay? Remember, the omega has to be the same. So if that hits you, you will probably break a jawbone, okay? It's the same thing when you think about area moment of inertia. The reason we care about this is it affects the stability of your craft. a hull that has cross-sectional area, water plane area, let's say 10 meters squared, versus you split the hull into 2 equal parts and spread them out. What is this configuration called? It's called a catamaran, all right? You have the same area, but what have you done to your stability? Intuitively, what do you say? You've substantially increased your stability just by splitting that area and moving it out, okay? Same thing as fist hitting you in the jaw, all right? The area, the axis of rotation is my midline, but now the area is much farther out from the midline. So the area moment of inertia is much higher. If that's the case, the stability is much higher. And we'll see how this, we'll talk about the exact formulas that you use to compute stability. All right. Okay, so area moment of inertia is, it is a geometric property that indicates how the points or area of an object are distributed with respect to a particular axis. Ugh. And do not confuse this mass moment of inertia. We use the same symbol to represent both, but from context, usually it becomes clear whether it's mass moment of inertia or area moment of inertia. Do not confuse mass moment of inertia. All right. And this property is useful. It's useful for hull stability calculations. Based on the water plane area. I was going to say something, but I forgot. Oh, yeah. Notice here, it says distributed with respect to a particular axis. Okay. Now you can look at my webcam and let's talk about this stapler. Hey, where are you? You're here. Okay. So stapler. Let's say I'm spinning the stapler about the long axis. Okay, about this long axis. So it's spinning like this. And if it hits somebody standing nearby, no big deal, right? Now we have the stapler spinning about this axis with the same angular velocity. Now if it hits somebody here, a slightly bigger deal, okay? So moment of inertia is always defined about a particular axis. So keep that in mind. All right, analytical definition is XX We also call this Ix. It's double integral of y squared dx dy, and Iy is double integral of x squared dx dy. And remember, these correspond to axes. So moment of inertia about x-axis, moment of inertia about y-axis. And let's take a very simple shape, a rectangle, and first let's talk about. Yeah, first let's talk about the one of the axes that goes through the center of area, the centroid, and then the other guy. If this plane rectangle rotates about the x-axis, we call this we basically want to compute Ix. If it rotates about the other axis, we want to talk about Iy. Great. And I'll tell you more about why it's y squared, why it's x squared. One more thing to keep in mind: this dx times dy is d area. Okay, so this is the infinitesimal area. Fine. Now, let's think about Ix. Forget about Iy. Let's talk about Ix first. It's y squared dx dy. Ix means we are rotating about the x-axis. So the hull is doing this. Okay? It might be in roll. And Iy would be when you're pitching up and down. Okay? Now, when you're rolling, you want to figure out how far the area is distributed from your center line. That's my center line, the x-axis. How far, if we cut a small area, let's say a small square here, how far is this from the x-axis? What's the coordinate? Yeah, it's the y coordinate, okay? So that's why you have y squared times area, okay? Same thing, if you talk about how far this tiny square cut is from the y-axis, you think about the x coordinate. So the distance squared is the x squared part times the area. When you talk about I mass, the mass moment of inertia, it's the same. It's r squared times dm, okay? So it's completely equivalent. You just figure out how far from the axis, that's your r. If we talk about the y-axis, if you talk about the x-axis, the distance is y, so r squared is y squared. In the other case, it's x squared. Okay, so if sometimes it might feel like there's a typo, this should be Iy, this should be Ix. No, that's not right. This corresponds to which axis you're rotating about. Okay, and let's do an example. So let's start with a very simple shape that you've dealt with many times in statics, dynamics, etc. So let's talk about a rectangle. So what is the Ix, Iy for a rectangle? talking about rectangles is not completely useless. I mean, if you think about a barge, if you're designing a barge, the cross section is basically a rectangle. And the water plane area would be more or less a rectangle. What should I write? Ix equals? We need to evaluate the integral to get like a single number. Well, in terms of b and h, but a single number. So what should I write here? The formula is here. How do we use this formula for our rectangle? I mean, the insides we can copy paste, but what's the limits on the integration? Zero to b over 2, 0 to h over 2. Does that cover the whole rectangle?
No, it would be negative b over 2 to b over 2 and negative h over 2 to h over 2.
Yeah, that makes life easy for us, right? For x, we'll say we'll go from minus b over 2 to plus b over 2. In the y direction, we go from minus h over 2 to plus h over 2. So let's do y equal minus h over 2 to y equal h over 2. X goes from minus b over 2 to, and inside we have the same y squared dx dy. All right, here, since y and x are not dependent on each other, we can do either of the integrations first. Either do dx first or dy first. So let's do dx first. So the y part remains the same, minus h over 2 to h over 2. And all right, you tell me, what should I put in here? Yeah, x going from minus to plus, and dy remains. So we've just evaluated the dx integral. There's no x term in here, so constant becomes x. And let's go one more step and we're done. Okay, so this is minus h over 2 to h over 2. Y squared, when you plug this in, b over 2 minus b over 2 becomes b times dy. Okay, and what is this? B times y cubed over 3 minus h over 2 to h over 2. Have you seen this before?
Yes.
This is h over 2 whole cubed minus negative h over 2 whole cubed. B over 3, what is this? H cubed over 4, right? So times h cubed over 4. BH cubed over 12. Probably use this over and over in your statics class. Okay, and hopefully they showed you the same thing, where it comes from. So that's Ix, okay? So you see that's where all of these, maybe you were given tables of these. So all of them, you have to do the integration to figure out what the value is. What would you write for Iy? So similarly, for Iy, what would you say? What's the integral look like?
Just a quick comment. When you do your double integrals, you have the limits. The first integral is the limits of y, and then the second integral is the limits of x, and then you go y squared, and then you go dx and dy. I've noticed other Indian professors do that. I think in the US, we would have written that as, no, I guess you got it right. Never mind. Sorry about that. Seems like sometimes they have that backwards, whether the dx and the dy in their order.
All right. Yeah,
Sorry.
but it doesn't matter. Even if you write dy and dx, because if y were dependent on x, then it would matter which integral you do first. But here it doesn't. Okay. All right. So similarly for Iy, what would you write? Just it looks very similar to this. So what would you say? The only change is instead of a y squared, we have an x squared. Okay. And the limits, we still want to cover the whole rectangle. So the limits would be the same. All right, negative h over 2 to h over 2. So we have y going from minus h over 2 to h over 2. X going from minus b over 2 to b over 2. And so y squared, we have x squared dx dy. When you evaluate this, what will you get? Instead of bh cubed over 12, what do you get instead? Yeah, hb cubed over 12. All right, so we have hb cubed over 12. It has to be symmetric, right? See, because moment of inertia doesn't care about which one we specify to be the x-axis, which one we specify to be the y-axis. It could just easily have been swapped, right? So in that case, this would have been our b, and the other one would have been our h. So it has to be symmetric. All right, perfect. So this is how you do it analytically. Can we do the same thing numerically? What would you change? Yeah, instead of integrals, we do two summations. And this small tiny cut, basically there's, let's say a few hundred small tiny cuts, and we have to sum them all up, all right? So let's do the same. Doing the same computation numerically. So first thing we need to do is discretize our object. Oh, and we're out of time. So we'll do this next class. Any questions? All right, see you next week. I put up homework where you basically use all of this stuff. So take a look and ask me questions next week.